remember at the end last time, we substituted a power series proposed solution for VEL into the radial equation transformed into the variable rho. And what we got was the following upon that substitution. Sum from k equals minus 1 to infinity of c sub k plus 1 times k plus L plus 2 times k plus L plus 1 times rho to the k plus L minus the sum from k equals 0 to infinity of 2ck times k plus L plus 1 times rho to the k plus L plus the sum from k equals 0 to infinity of e squared times lambda times c sub k rho to the k plus L. Finally, minus the sum from k equals minus 1 to infinity of L plus 1 c sub k plus 1 rho to the k plus L is equal to 0. That glorious beast is what we get by substituting. Yes?
Should that person be indexed for minus 1?
Yes, it should. Thank you. K from minus 1 to infinity, yeah, because we want the first coefficient to be c sub 0 in all of those summations. And in fact, it is. And so notice that by changing the index to go from minus 1 to infinity instead of 0 to infinity in the first and the last term has caused rho to the k plus L to appear as the exponent involving rho in all of those terms. And so this has to be 0 for all rho. And the only way that can happen is if the coefficient of every power of rho is equal to 0. Otherwise, that wouldn't happen. For a polynomial to vanish, for all values of x, if it's a polynomial of x, all the coefficients have to be 0. So for this to vanish for all rho, coefficients of each power of rho must themselves vanish. That's the only way to do that. So that means we can collect all those things which are multiplying rho to the k plus L and set it equal to 0. And this gives us what we call the recursion relation. That collects ck plus 1 terms together. ck plus 1, this is not ck plus L, this is ck plus 1 down there as well. So c sub k plus L is what appears in both the first and the last sum. ck plus 1 times k plus L plus 2 times k plus L plus 1 minus L times L plus 1. So I collected the things that multiply ck plus, well, actually I collected the things that multiply rho to the k plus L in the first term and the last term together, and then factored out ck plus 1. So this is just the coefficient of rho to the k plus L coming from the first and the last summations. That's ck plus 1 times k plus L plus 2 times k plus L plus 1 minus L times L plus 1. And then for the other two terms, we're going to get minus c sub k times the quantity 2 times quantity k plus L plus 1 minus E squared times lambda, that has to add up to 0. So that is, for each value of k, that is what overall has multiplied rho to the k plus L. That has to be 0 for every value of k. And so therefore, this is what you get as a result of that. Okay? Any questions? And that means there's a relationship between C sub k and C sub k plus 1. That's the big picture here. So in other words, this says that, right over here, this says that ck plus 1 divided by ck is equal to minus E squared times lambda plus 2 times k plus L plus 1 divided by k plus L plus 2 times k plus L plus 1 minus L times L plus 1. So the idea is that this allows me to get all of the coefficients if I know one of them. If I know C sub 0, this would allow me to find C sub 1. And if I then know C sub 1, it allows me to find C sub 2. And if I know C sub 2, it allows me to find C sub 3, and so forth. So this is a relation which implicitly tells us every coefficient in the entire power series if we know the value of C sub 0. It would take forever to do that if there were an infinite number of terms, but this implicitly gives us all of them if we know the first one. And in fact, really we can arbitrarily set C sub 0 because the wave function would only be determined up to an overall normalization, so we could set C0 by requiring the wave function to be normalized, and you get to do that sort of thing in the homework. So let's show that C0 in fact is arbitrary here. So what about C0? Well, two of these sums start with k is equal to minus 1. For k equals minus 1, only two of the summations contribute. A term, since the others start at k equals 0. And if you look at the contributions for k equals minus 1 from the first term and the last term. So the first term says for k equals minus 1, C sub 0 times L plus 1 times L. That's what you get if you put k equals minus 1 into those two terms. C0 times L plus 1, because this is minus 1 plus L plus 2, which is L plus 1. This is k plus L plus 1 would be minus 1 plus L plus 1 is L. So the first piece says that C0 times L plus 1 times L. And then for the second, for the last term over here, if I put in k equals minus 1, I'm going to get just C0, because this doesn't have k in it, C0 times L plus 1 with a minus in front. equals 0. C naught times L plus 1 times L minus C naught times L plus 1 is equal to 0. What condition does that put on C naught? None. It doesn't put any condition on C naught. Because that's identically 0. It doesn't matter what C naught is, that's identically 0. So that says C naught is arbitrary, and in fact, we're free to set it by normalization. This shouldn't be surprising because what we got, remember, was a differential equation. It was this linear differential equation for this function, and you said left-hand side applied to the function equals 0. Well, if you multiply the function by some constant, then you'd be multiplying both sides of the equation by a constant. So you'd be applying, on the right side, you'd be multiplying 0 by a constant. You'd still have a solution. So for a linear homogeneous differential equation like that, any multiple of a solution is another solution, and that's really all this is reflecting. That you can multiply the solution by any constant, and it'll still be a solution of that homogeneous differential equation. And this is what we want, because we want to have the freedom to normalize our wave function. Any questions? So, any questions? All right. Let's look what happens as k goes to infinity. As k goes to infinity, we've got ck plus 1 over ck goes to, well, as k goes to infinity, lambda is just a constant, and e squared is just a constant. It's just charge on the electron squared. So as k goes to infinity, what does the numerator approach for all intents and purposes? 2k. 2k, right? And how about the denominator? K squared. K squared, yeah, because as k goes to infinity, L and 2 and 1 and e squared, lambda, all that stuff just become negligible compared to k itself. So as k goes to infinity, that ratio approaches 2k over k squared, or in other words, it approaches 2 over k, which looks innocuous enough, except that this is the behavior of the power series for a e to the 2 rho as k goes to infinity. Because, first of all, what's the power series for e to the x? If I do a Taylor series expansion of e to the x to get an infinite polynomial, if you will, to represent it, what does that look like? I'll start it for you. E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, 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 dot. In other words, x to the n over n factorial is the, and are the terms in that power series. Or in other words, it's equal to the sum from n equals 0 to infinity of x to the n over n factorial. That's the power series expansion of e to the x. So e to the 2 rho times a would be k sum from k equals 0 to infinity of 1 over k factorial to rho to the k. So I'm just using k as my summation index there, and using 2 rho in place of x. So a e to the 2 rho as a power series is a times sum from k equals 0 to infinity of 1 over k factorial 2 rho to the power of k. So in that power series, c sub k is 2 to the k over k factorial times a. If I think of this as a power series in rho, this is 2 to the k over k factorial, rho to the k, just breaking out 2 rho to the k is 2 to the k rho to the k. So if I think of this as a power series k equals 0 to infinity of c sub k rho to the k, then c sub k is a times 2 to the k over k factorial. I'm not done yet. That's not the punchline yet, but I'm just saying that if I do a power series of e to the 2 rho, then the coefficients in the of a e to the 2 rho, the coefficients in the power series are a 2 to the k over k factorial. So therefore, ck plus 1 over ck is equal to 2 to the k plus 1 over k plus 1 factorial, and then divided by 2 to the k over k factorial, or in other words, times k factorial over 2 to the k. What's 2 to the k plus 1 over 2 to the k? 2. And what is k factorial over k plus 1 factorial? 1 over k plus 1, right? So that looks like 2 over k plus 1, but that certainly approaches 2 over k as k goes to infinity. So in other words, the power series for a e to the 2 rho as k goes to infinity also has the property that ck plus 1 over ck goes like 2 over k as k goes to infinity. So our power series for VEL has the same asymptotic behavior at infinity, so to speak, in the power series. The same asymptotic behavior of the coefficients as e to the 2 rho does. And you say, okay, so what? Well, the so what is that would make the wave function not normalizable. This is a problem, since then we have that our UEL, because remember we were looking at UEL, that UEL was defined to be e to the minus rho times VEL. Actually, our VEL is defined by UEL as e to the minus rho times VEL. But then our VEL, we have discovered, has the asymptotic value of a e to the 2 rho, so therefore this would look like e to the minus rho times a e to the 2 rho, because VEL behaves like a e to the 2 rho. which would look like a e to the rho, which would do what as rho goes to infinity? What does a e to the rho do as rho goes to infinity? It goes to infinity. And that would mean cannot normalize psi.
You're missing another O at rho.
What's that? Oh, yeah, thank you, yes. As rho goes to 0 times 0. As rho goes to infinity. Yes. Yeah, as rho goes to 0 over 0, well, that's sort of finite, sort of not finite, whatever. Anyway, as rho goes to infinity is what I certainly meant to say. So that would mean you can't normalize psi, which would make psi unacceptable, as we know. But then again, that's not too surprising, because all this is saying is if I pick an arbitrary energy, because remember lambda has code for the energy in it, if I pick an arbitrary energy, I get a wave function which isn't normalized. I get a solution of the Schrodinger equation for any arbitrary energy I pick, but the solution cannot be normalized, which makes it an unacceptable solution. But that's not surprising because it's the what that put the what in what? It's the boundary conditions that put the quantum into quantum mechanics. So in other words, most solutions for an arbitrary energy don't satisfy the boundary conditions. They're not normalizable. So how can we avoid this? How can we keep having this from happening? We can avoid it by having k not ever get to infinity. Or in other words, we can avoid this if our series terminates. If ck plus 1 is equal to 0 for some value of k. Because if ck plus 1 is 0, what's ck plus 2? 0. And what's ck plus 3? 0. Because the recursion relation says if you ever have a ck which is 0, every other ck after it is also 0. Because ck plus 1 is a multiple of ck. So if you have any of those coefficients be 0, everyone after it is also 0. So we can avoid this problem if the series terminates, because then it's not even an issue of what happens to ck plus 1 over ck, because they're all 0 out past a certain value of k. So, in other words, for the wave function to be normalizable, the series has to terminate, and we'll see that puts conditions on the energy. To avoid this trouble, the series must terminate. Terminate. Oh yeah, exterminate, that's right, exterminate. I have a sister who's a huge Doctor Who fan.
You're thinking of Arnold Schwarzenegger.
Yeah, right, I'm thinking of, I'll be back, the Terminator. Right, no, exterminate. Craig Ferguson on his late night show recently had a Doctor Who day. And I guess it was his monologue, or talking to one of the guests or whatever, he said that if you've ever seen a Dalek, how many of you have ever seen a Dalek before? You know what I'm talking about? Okay, a few of you have. The Daleks are these evil robot aliens. They're supposed to be really scary, but they look like vacuum cleaners or whatever. But anyway, they roll around on these wheels. And so Craig Ferguson says, so if you ever are attacked by a Dalek, just run upstairs because they're on wheels. But then apparently he said the BBC figured that out, and so later versions of the Daleks could fly, so that they could get people even if. So they're supposed to be terrifying, but I know the school that they're about as terrifying as a bad vacuum cleaner. It's just. But anyway, so I must terminate is what our series has to do for some value of k. For some k max. There has to be some k max, the last non-zero coefficient. So if C sub k max plus 1 equals 0, all subsequent CKs are 0. That's the idea there. If one of these guys is ever 0, boom, all the other ones are 0 after that. Any questions? How can we make that happen? That's easy. Make the numerator 0. But lambda, remember, contains the energy in it. Our definition of lambda had the energy in it, so this is going to be a condition on the energies. This will happen if E squared lambda is equal to 2 times K max plus L plus 1. Because if that's true, then CK max plus 1 will be equal to 0. Let's define K max plus L plus 1, which will be an integer because the K's are integers, and L we know is an integer because it's the angular momentum quantum number, and orbital angular momentum has integer values of the orbital angular momentum quantum number. 1, last time I checked, was an integer, so K max plus L plus 1 is an integer. Let's call that integer, oh, I don't know, N. Where N is the, what should we call N? Maybe the principal quantum number, just to come up with a name for it. So I'm going to leave that there because I'm going to come back to it again, so I might as well just leave it up there. So now let's put the definition of lambda back in. So this is saying that E squared over 4 pi epsilon naught times 2m over h bar squared w, w being the binding energy, to the 1/2 is equal to 2n. So I just plugged in the definition we made of lambda. W is the binding energy, which is positive because it's minus the actual energy, and we're looking for bound states which have negative energies. So this says, if we rearrange a bit, that E squared over 4 pi epsilon naught divided by 2n, that quantity squared is equal to h bar squared times w divided by 2m. So in other words, I just took the h bar squared w, over 2m to the 1/2 to the other side, just multiplied, flipped it over, took it to the other side, and then divided by 2n and squared in order to undo the 1/2 there. Right, everybody happy with that? Or, in other words, E, which is minus W, is equal to minus m over 2h bar squared times E squared over 4 pi epsilon naught, the quantity squared, times 1 over n squared. The energy goes like some minus thing times 1 over n squared. And if you plug in all those values and convert to electron volts in the result, what do you guess you get? 13.6. That magic number 13.6, this is equal to minus 13.6 electron volts divided by n squared. It's the Bohr energies. Oh, sorry, that's not very big a bite. Hey, look, it's the Bohr energies. It's the energies that come out of the Bohr model. Check that out. So to keep the wave function from to keep it from blowing up, to make it normalizable, the series has to terminate. That coefficient gets folded into this integer n, and the energies are minus 13.6 electron volts over n squared. So the Schrodinger equation successfully predicts the observed energies for hydrogen. Now, we'd like to know that it does the right thing in terms of the values that are allowed of n. So let's go back again. So we said that n by definition was k max plus L plus 1. So what would be the possible values for k max? Well, maybe the second coefficient vanishes. Maybe C1 is equal to 0, in which case k max would be, k max would be 0 in that case. Because the series starts with C naught, and then there's a C1 term, a C2 term. So you could arrange things so that the denominator up here, when I plugged in k is equal to 0, you could make the denominator go away, and then k max would be 0 in that case. Or you could decide I want the series to terminate after C1. I want C2 to be 0. So then you would just make lambda be whatever it takes in order to make this equal to 0 when I plug k equals 1 in here. And then that would mean C sub 2 was equal to 0. And so on and so forth. So in other words, k max can be any integer we choose. We choose lambda to make the numerator go away, and then that makes the series terminate. So we can choose any value of k max we like by choosing lambda to make k max equal to that value. We choose k max by making lambda whatever it needs to be to make numerator equal 0 for that k, for that value of k. That's up to us. So we can choose lambdas to make k max anything we like. So if k max is equal to 0, suppose we arrange to make lambda, really we're finding the value of lambda, we should say, we're finding the value of lambda which makes k max be 0, then what are the values of n that could go with that? Well, what are the possible values of L? Remember, it's the orbital angular momentum quantum number, the one associated with L squared. The eigenvalues are L plus 1 h bar squared of the L squared operator. What are the possible values of L for orbital angular momentum? We're not there yet. So yeah, it's going to say 0 to n minus 1, but I'm about to derive that L goes from 0 to n minus 1. But right now I'm going the other direction. I'm starting with L and figuring out what I'm figuring out what n values can go with various L's. You'll see what I mean in a minute. So just first principles, before we did any of this, what are the allowed values of the orbital angular momentum quantum number L? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1,047, 1,048, 5,467 billion integers. Any integer you like. Then n can be, well, I'll say it like this. So then n equals L plus 1 can be 1 or 2 or 3 ... since L can be 0 max is 0, then the allowed values of n that could go with that are 1, 2, 3, and so forth, because n in every case is L plus 1, and L can be 0 or 1 or 2, in which case n can be 0 plus 1, 1 plus 1, 2 plus 1, 1, 2, 3, 4, 5, 6, 7, and so forth. If k max were equal to 1, then n equals L plus 1 can be what values? I'm sorry, I got this wrong. N is not L plus 1 in this case. N is what in this case? If k max is 1, what is n? L plus 2, because it's k max plus L plus 1. Then n equals L plus 2 can be what possible values? 2, 3, 4, 5, because L can be 0, 1, 2, so therefore n can be 2, 3, 4, etc. I'm just looking for the pattern here. If k max is 2, then n will be it can be 3, but not just 3. So I'm like, instead of being L plus 2, n will be L plus 3, right? L plus 3. N equals L plus 3. So it can be 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Don't forget 2,906. And certainly 4,097 wants to be in there, and so on and so forth. So obviously we can continue this forever. So in the grand scheme of things, n can be any positive integer. That's really what we're concluding here. Is n can be any positive integer. And now we're going to turn it around and say, okay, well, what if we start with n instead of with k max? So n can be any positive integer n equals 1, 2, 3, 4. Note that n can't be 0. N has to start with 1. Because at the least, n is L plus 1. That's the smallest it can possibly be is L plus 1. So n has to at least be 1. So now we turn it around and get the relation that you're more familiar with. At each value of n, if we start with n, because we got it out of k max, but k max isn't a very natural way to look at it. It's more natural to look at n because n is what determines the energies. K max plus L plus 1 is what determines the energies. At each value of n, the allowed values of L are, well, L, if we turn this around, L is n minus k max minus 1. So that'll be, well, I'll erase that and say, okay, so what will we start with? What's the smallest possible value of k max? 0. K max could be 0. C0 might be the only non-zero coefficient in our power series. So k max could be 0, in which case L would be n minus 1. What's the next smallest possible value of k max? 1, in which case L would be n minus 2. Dot, dot, dot. Where does this stop? 0, because can I have L is equal to minus 1? No, that's not the way angular momentum works. So in other words, L goes from n minus 1 to 0. That's the relation you're more familiar with. We usually start with n and then say L goes from 0 to n minus 1. But that comes from turning around the relationship that we really started with, which was in terms of k max, and figuring out what can n be in terms of all the various k maxes and L's. So here this is because since k max is equal to 0, 1, 2, etc., and we know L has to be greater than or equal to 0, so therefore that has to stop with L is equal to 0. We can't keep going with that. So this is the relation that you come to know and love from the past, the idea that, excuse me, that for a given value of n, L goes from 0 to n minus 1 as its possibilities. And then that means our formula over here can be further embellished a little bit, where we say that then E sub n is equal to minus all that crap, which I'll just say minus 13.6 electron volts over n squared, where n is equal to 1, 2, 3, dot, dot, dot. So we had established before what values n could take when we just said n was k max plus L plus 1. Careful consideration says n can be 1, 2, 3, and so forth. And then we can make a tree, and L, M. So if n is equal to 1, what values of L could go with that n? Just 0, right? Because it goes from 0 to n minus 1. Just 0. What values of the other quantum number, that m, which will sometimes we leave undecorated, sometimes we call it m sub L to emphasize it's associated with orbital angular momentum. What are the values of m, or m sub L, that can go with L is equal to 0? Well, m goes from what to what? Minus L to L in steps of 1, so in this case that's minus 0 to 0, or in other words, m sub L has to be 0. If n is equal to 2, what values of L are possible? 0 and 1, right. So we could have 0 or 1 in that case. If L is 0, m has to be 0, but if L is 1, m can be 1, 0, minus 1. And then we could keep going. If we make n is equal to 3, then L could be 0, 1, or 2. And for the L equals 2 states, we can have 5 sublevels. Minus 2, minus 1, 0, 1, 2, and so forth. And so we put subscripts on the overall wave function that you construct out of all of this to indicate the psi n sub n ln. So it gives you the n, the l, and the m value. Here I'm leaving the m undecorated. So you've got psi 1, 0, 0, psi 2, 0, 0, psi 2, 1, 1, psi 2, 1, 0, psi 2, 1, minus 1, which I discovered is leading to confusion in the book by people say, what? What is psi 2, 1, dash 1? No, that's psi 2, comma 1, comma minus 1. We often just don't bother with separating with commas. So if you see psi 2, 1, dash 1, no, that's psi n equals 2, L equals 1, m equals minus 1 is what that stands for. And so forth. So the ground state is the one with the lowest energy. That's the one with n is equal to 1. So psi 1, 0, 0 is the ground state. How do the energies of these guys compare to one another? How do the energies of psi 2, 0, 0, psi 2, 1, 1, psi 2, 1, 0, psi 2, 1, minus 1 compare to each other? They're equal. According to what we've said so far, and all we're going to say in this course, they're equal to one another. now it turns out there's what is called the spin-orbit coupling of the electron and the proton that leads to breaking of this degeneracy. So it's actually more complicated than this. But to lowest order, if you ignore the contribution of spin to the energy, then all these guys have the same energy because the energies only depend on the principal quantum number n. They don't care about L and M. You can also break that degeneracy by putting the atom in a magnetic field, which we talked about some in Physics 280, in a kind of hand-wavy way. We wrote down the Landé G factor and said, and it turns out that, and if you do perturbation theory, you can actually get the term, and it turns out that into, and so now we see that, but we're not going to do that here. Unless I can do all the quantum 2 next week. Do you want to try that? I don't either, actually, it turns out. That would be kind of unrealistic. Yeah, so kind of there's our punchline. Look, it's hydrogen, hooray! And I guess...
Why do I hear some booing in the background?
Because that's the voices in your head.
Yes.
Yeah.
Maybe it's because someone said that Bohr's model works, but it doesn't deserve it to.
Yeah, but this isn't Bohr's model anymore. This is Schrödinger. This deserves to work.
Oh, yes.
Right? Yeah, this fully deserves to work. So that's boo. Those boos are coming from Bohr in your head.
Ah,
Yes.
getting